geogebra.org, and then awaits further instructions. Okay? Thank you, DK. And I also said you're not signing in. Okay. So I'm going to show you what's going to happen on here before I tell you to actually how to get into yours. So you have created on your paper either a sine or a cosine graph, right? Remember, it's very different than the unit circle. These are functions that have an input of the angle. Everybody has the same angles as the input. Your output is depending upon whether you were taking the sine value or the cosine value. Okay, does that make sense? It's a very different concept than the unit circle itself. So depending on which one you did, like if you have cosine sitting in front of you right now, then on the computer you're going to do sine and vice versa. And this is what it's going to look like. So everybody's going to have a screen that looks something like this. First of all, you do not want to hit this button or this, or it's going to reset everything and you're going to be mad and you're going to have to start over. Okay, so just don't push those and you'll be fine. You're going to be able to control this point here. And I can rotate this point around the circle. You see how that moves over there. Each little point is a special angle. It includes the pi 12ths, which we don't care about. You can do pi 12ths if you want, but you don't have to. Just like you did on your paper, we started with pi 6. So I'm going to rotate. I could not get it to do pi over 6. It's a programming thing. I can only do 1/6 pi. So you would never really write it that way, but you're just going to have to know that that's right. And we know that if this is half of a unit, this is my sine value, this is my cosine value. Okay, so this one's only going to show your sine values over there because that's the way I have it set up. You're going to literally do fettuccine just like you did on the paper. So once I wrote a pi 6, and I see this little piece of fettuccine here, I'm going to click insert fettuccine. And then I'm going to rotate to pi 4ths. And then I'm going to insert fettuccine. And then I'm going to rotate to pi 3rds. And I'm going to insert fettuccine. Does that make sense? It's going to go a lot faster than it did on the paper. You're doing the same thing, but with the other graph. Okay? So if you end up getting cosine, when I rotate this to pi 6, again, still yellow is sine, blue is cosine, but the cosine is what's going to pop up over there. The cosine of 0 is 1. So I can insert a piece of fettuccine right there, move on to pi 6, insert fettuccine all the way down to 2 pi. Okay, does that make sense? Everybody understand what to do? So on the left-hand screen, the left-hand side of the screen, on GeoGebra, it says like classroom, I think. There's something that says classroom over there? I literally said don't sign in. Multiple times. So you are 5th period. So once you go to classroom, there's a place for you to enter a code. If you have cosine sitting in front of you, you do sine and vice versa. Once you enter this, it'll ask you again, do you want to sign in or do you just want to put your name? Just put your name because it doesn't let you sign in. It's going to make you create an account. You don't need to do that. So just put your name and it'll be good enough. And then go in there and insert your fettuccines. I know when you do this, it looks like DNA. I keep hearing that. Remember that the point of the fettuccine is to get it that distance away from the x-axis. We're actually plotting points that's at the end of the fettuccine. Those little line segments don't really exist on there. Okay? So enter your fettuccine. What are you doing, dear? geogebra.org. Classroom on the left-hand side. Did not say that. Okay, so the reason I had you break actual pieces of fettuccine and then do some digital ones here is so that you could see that all these measurements are coming from the unit circle. We are unrolling the unit circle to come up with these functions. But we're taking the unit circle that had our x and y values were both functions of theta to where it's an actual function where we have an input of an angle and the output is either sine or cosine. We're not getting them both in the same graph. Okay? Once you make it all the way around your circle, your screen should look like one of these two, depending on which one you did, right? Which should look very much like what you have on your table, but a little bit different. Let me make sure I get everybody enough. No, don't. I told you, don't push those buttons. Those are bad things. Uh-huh. Well, why'd you do that? Click on wait. and then reload. You probably have to reload. And so it's okay. You just put, like, apparently it was responding and you didn't know it. And so it just stacked a bunch of them next to each other. Don't worry about it. Oh, there you go. There you go. Okay. So do we have our fettuccines on there almost? Well, it's supposed to, because you did cosine on your table, you were supposed to be doing sine. Okay. So what the box I do want you to click now that we have our fettuccines on there, right up here by the 1 on the y-axis, bless you, click that box. It should put a little check mark in there. Then take your point and slowly rotate your point around the circle again. You don't have to stop this time. You just click that box and then slowly rotate your point around the circle and see what happens. Yes, you want to go slowly or it's not going to. And when you go, the slower you go, the more solid it will be, but it's basically putting the string on there for you. It's connecting all those points. So now you click that and then rotate your point again. Just kind of rotate it slowly around. Yeah. You can go either direction, it doesn't matter. And so you put on there just, what, how many? 3, 6, 9, 12, 14 pieces of fettuccine, but the dots that are getting plotted or the points that are getting plotted when you're rotating this, it's all the ones in between. So you can see what's really happening with that sine curve. As your angle, so if this is my sine, as the angles go from 0 to pi halves, it's increasing, then it's decreasing from pi halves to pi. And if you go really, really slow or keep going back over, it can be solid. You don't have to make it solid, that's fine. I did so you could see what was happening there. So do you see some similarities between the graph that's on your screen and the graph that's on your table? Yes, so they're similar, but they're not the same, right? These are both called sinusoidal curves, even though one of them is cosine, because really we could get away with only talking about sine. We use cosine because it makes some things a little bit simpler, but we don't necessarily even need the cosine curve. They are so similar. What do you think I could do with the cosine curve to make it look like the sine curve? Okay, so if I reflect it, it would look like this. I can shift it, yes. So if I look at, you see how this is the top of the hill? This is the top of the hill here is at pi halves. The top of the hill here is at 0. If I shift this over, oops, well, let me get the right thing that I want here. If I shift this over to where my axis is like at pi halves, do you see how they're the same now? So the cosine function is really just a shift of pi halves of the sine function, okay? But instead of having to worry about shifts, we can look at sine and cosine differently. So lots of similarities, look very, very similar to each other, but obviously they're not exactly the same. All right, we got all that? All right, so you have a basic idea of what the sine and cosine curves look like at this point, right? All right, so let's close our tablets, grab the piece of paper that I gave you, and let's graph some parent functions. And before we graph them, we need to talk about number families. Again, I think we talked about these a little bit last semester for something that we did. But we're going to have to refer to these, so I want to make sure you know what the heck is going on. So this represents all of the real numbers. In the real number world, we have irrational numbers that can't be written as fractions and rational numbers that can be. In the rational number world, we start on the inside with natural numbers. They're your counting numbers starting with 1. 1, 2, 3, 4, 5, 6, 7. Whole numbers are your natural numbers plus 0. Integers are positive and negative whole numbers. So that's positive and negative counting numbers, including 0. And then rational numbers obviously can be written as fractions. So it is important to understand, sometimes this wording and these questions come up on random placement tests and different things like that. The reason we're talking about it right now is so that we know what the letters are. I'll be honest, I don't remember what they are unless I look them up, but we're going to use it, so I want to make sure you know what we're talking about. We're going to be talking about the integers, and they're represented by these weird-looking capital letters that I know it's kind of blurry, you can't hardly even see, but it's a capital Z, but it's like doubled like that, so that represents the family of integers. Okay, so we're going to use that. Just want to make sure you know what we're talking about there. Okay. All right, so on the paper I gave you, there's a place for tangent. We're not doing tangent right now, so don't worry about it. There is a nice, pretty unit circle with all of your values that you should know. And I want to remind you again, yes, we have an x-axis and a y-axis in quadrants 1, 2, 3, and 4, but this is a completely different kind of graph than the functions that we just created with our fettuccine. All right? Yes, on those graphs that you have in front of you, there's the quadrants 1, 2, 3, and 4, but we're really less concerned about those quadrants than these. If I ask you, is sine positive or negative in the second quadrant, we're talking about the unit circle. Because in the second quadrant on what you have in front of you, it's positive and negative depending on when you're talking about it. You with me on that? So we don't really care about that. We're talking about the unit circle values. So you've got to make sure that you've kind of kept those separate and know that they're two completely different things that are very much related to each other, but they're different kinds of graphs. Okay, so let's look at sine. Find your sine graph on there. The parent function for sine is just f of x equals sine of x. Okay? And we're not going to plot as many points as we did fettuccine on here because some of those numbers are not so pretty. I don't want the square root numbers or whatever. But I do know things about sine. I know that, first of all, my input's the angle measure, my output's the sine value. Cosine has nothing to do with this. If my input is 0, what is the sine of 0? 0. What other angle measures have a sine value of 0? Pi and negative pi. Negative 2 pi and 2 pi, exactly. Okay, right there on the x-axis when you're thinking about the unit circle. Like, you're still going to need to be able to picture your unit circle and think about that x and y-axis and those quadrants, but we're translating it onto here a little bit different. So those are all the times between negative 2 pi and 2 pi that sine is 0. And if you notice here, I've got, this is 0, this is pi, so halfway is pi halves, and this is pi fourths. I don't even have a pi 6 and a pi thirds on here to graph. And that's fine, because we don't need it all. We know basically what it looks like, and we'll just get some important points on here. So halfway between 0 and pi is pi halves. What's the sine of pi halves? 1. Sine of pi halves is 1. Halves is over here. What's the sine of 3 pi halves? Negative 1. What's the sine of negative pi halves? Negative pi halves. Negative 1. And negative 3 pi halves would be 1. Okay. See why I was trying to drill these values into your brain? You need to just you need to know them. And we're putting them on here like this, and now that's really all I need because I know what the general shape is, and I can sketch in my curve to look something like this. And we went on your paper, you did from negative 2 pi to 2 pi, but we could have kept going, right? So we're going to put arrows on the end because it can just keep on going. When we start graphing these and translating them, I am not going to help you even one little bit if you do not have the little parent function sketched. I'm not even going to tell you why I'm not going to help you. I'm just going to tell you to go away. Because that's why you don't know what you're doing, because you didn't sketch the little parent function. Okay? So here's what you got to have sketched. So the x and y axis, and then just one cycle of the sine function. And you've got, for this piece, you have 3 points that are at 0, ones that at 1, ones at negative 1. You need that every time you're going to go to graph a sine function. It will make everything will be simple and make sense at that point. Okay? We have, so when you did the digital fettuccine, we just went from 0 to 2 pi because that was one cycle, basically. This is 2 cycles because this is the shape and then it starts over, right? And then it would start over again, it would start over again. So, you only have to have one of these and then things just repeat. All right, so let's talk about what we know about this function, or what we can figure out. What is the domain of this? Very good. Negative infinity to infinity. What is the range? Negative 1 to 1. Do we include those? Yes, because those are y values that I actually use, so they are definitely included. All right, so on the graph that we have right here in front of us, how many zeros did we graph? 5. How many actually exist in the function? Infinite. There's an infinite amount of them. There's 5 here, but if it keeps going, there's going to be an infinite amount of them, right? But they don't occur at every single point. So I can't say my zeros are from negative infinity to infinity, even though there's an infinite number of them. And clearly I can't list out an infinite number of them, right? But they occur every how often? Every pi, right? So I'm at 0, pi, 2 pi, negative pi. So like every domain of pi, I have another 0. So this is where that whole integer thing comes in. To determine our zeros, or to define them rather, we're going to have to say it's the set of all x's such that, let's scroll here, x is equal to n times pi, right? Because it happens every pi. But then I need to state, like, n can't be 1.5, and it can't be 0.2. It has to be a positive or negative integer. So then I say where, so comma, n is an element. This board makes everything boxy these days. Element. So it's like a flat C with a little line, kind of a weird looking E, of the integers. So that means n can be any integer. Negative 5 pi, negative 4 pi, negative 3 pi, positive 2 pi. It could be 0 even. Okay. Does that make sense why we have to say it that way? And that'll take care of the infinite amount of them. Do we have a y-intercept? Yes. What is it? 0, 0. Do we have any asymptotes? No. No asymptotes. Okay, amplitude. Amplitude is a new word. It's not that big of a deal. It is just, for the parent function, it is the distance between the x-axis and the maximum or minimum points. So it's just 1. So if I don't have any kind of stretch or compression, my amplitude is just 1. That's your generic amplitude there. The period is how long it takes to complete one cycle. So if I start here and I do the sine, I end there, that's where I would start to repeat. So it took me 2 pi units to complete one cycle. So the period for a sine parent function is 2 pi. We good with that? All right, so let's talk transformations. The A, B, C, and D do pretty much the same thing they've done in all the transformations. Some of them are called something a little bit different because it's trig, but they're really doing the exact same thing. So f of x is equal to a times the sine of b times x minus c plus d. So the amplitude is what we used to call the vertical stretch or compression. It's the same thing. Okay, so if there is no number in front of sine, my amplitude is 1 because that's the parent function. If my amplitude is 2, that means that basically I have a vertical stretch of 2, but it makes my amplitude the absolute value of a because the negative still does the reflections. So remember I said the period is the length of one cycle. And period and frequency are very much related. So the period is the length of one cycle. The frequency is how many cycles happen within what the generic period is supposed to be. So it's kind of the same formula, but just one is solved for one thing and one is solved for the other. So if I need the period to be able to graph it, the period is equal to 2 pi divided by the absolute value of b. The frequency is the absolute value of b, which you can easily get from a formula, but if you need it to put in the formula, then it's the absolute value of b is equal to 2 pi divided by whatever the period is. Kind of depends on what information you need. But these are the same thing. It's just one solved for one thing, one solved for the other. Okay. So your B is still your horizontal stretch or compression. Let's say that B was 3. Okay, that would mean it would be a horizontal compression because X still lies, right? So I would do 2 pi divided by 3. So that means my period is now 2 pi thirds. So it happens a lot faster. It happens in 2 pi thirds units instead of 2 pi units. So it still gets compressed. Okay. Your horizontal shift, C, is still your left and right. Just instead of calling it the horizontal shift, we call it a phase shift. So it has a fancy name, but it's still the same thing. Vertical shift is still called a vertical shift. It's still whatever D is. Midline is a new concept. We kind of treat it like an asymptote, but it's not an asymptote. Midline is what it sounds like. It's the line that goes through the middle of the function here. So in the parent function, the midline is y equals 0. If I do something and I do plus 3 and I've moved it up 3, my midline is now at y equals 3. Okay, so your midline really is just whatever D is. So midline is just y equals D. Any questions at this point? All right, let's check out cosine. All right, so cosine. I've got f of x equals cosine of x. So using information that we already know about the unit circle, what is the cosine of 0? 1. So when my input is 0, my output is 1, because I have cosine here. Where else between negative 2 pi and 2 pi is cosine going to be 1? Negative 2 pi and 2 pi. Because 2 pi and negative 2 pi, on the unit circle, that's right, that's exactly where 0 is, right? You're right back in the exact same spot. So I'm going to have a 1 at 2 pi and negative 2 pi. Where between negative 2 pi and 2 pi is cosine negative 1? Negative pi and pi. Very good. And then where is cosine 0? Pi over 2 and negative pi over 2 and 3 pi over 2. Exactly. All right. So we didn't have to worry about the square root answers or even the 1/2. We could just do the 1s and the 0s, get our points in the right spot, and then we know what the curve looks like. So when we sketch this in, it should look something like this. And notice when I put my arrows on the end, they're not pointing straight out, going off to Never Never Land, because it's going to curve back down, right? You need to be thinking when you do those things there. Your parent function that must be sketched in order for me to help you with anything is going to just be one cycle from 0 to 2 pi. So it would look like this for cosine. And then you have those 5 important points. You've got the 1, the negative 1, and the 2 zeros. And I promise you, if you do this, that graphing these is a piece of cake. If you try and just pull everything out of your brain and you have no idea what I've been trying to explain to you, you're not going to ever figure it out. There's always a method to my madness. Okay, so let's look at this. Do we have the same domain that we did for sine? Yes. Still going from negative infinity to infinity. Do I have the same range as I did for sine? Yes. So negative 1 to 1. All right, so zeros. Am I going to have an infinite amount of zeros again? Yes. Do they still happen at every pi units? Like, are they a pi apart? Yeah, they're still a pi apart. They're not on pi. It's just shifted, right? So I don't start at 0, so I can't say n times pi, because that would mean there'd be 1 at 0, right? But I've shifted to the right or to the left, depending on how you want to look at what all's going on here. and by pi halves, right? So it happens at pi halves, and then 3 pi halves, and that is pi apart. So it's still every pi, but I have to shift over to start. So it's going to look like this. It's the set of all x's such that x equals, it's still n times pi, because that means it's happening, they're pi units apart, but I'm going to put plus pi halves, because that way when I put in 0, that would start me at pi halves. Does that make sense to you? And then comma, where n is an element of the integers. And don't worry, you're not going to have to write that too many times, but you do need to understand the language behind it and what it means and why we have to write it that way. Okay? Do we have a y-intercept? Yes. What is it? 0, 1. Good. Do we have any asymptotes? Nope. What do you think the amplitude is? 1. What do you think the period is? 2 pi. So most of that is almost exactly like it was for sine, right? The only difference is we've shifted it over a little bit, so it changes the y-intercept and whatnot. So your transformations for cosine, like this. F of x is equal to a times cosine of b times x minus c plus d. Amplitude is still absolute value of a. Period is still 1 cycle. Frequency is the absolute value of b. Okay? And one of them leads you to the other one, depending on which direction you need to go, whether you're going from the formula or, from the equation or into the equation. So if I need to know what the period is, and I have the equation, that's going to be 2 pi divided by the absolute value of b. If I have the graph, so I know the period, but I need b to write the equation, then to find b, that's going to be 2 pi divided by the period. Your horizontal or phase shift, your left and right, is still c, like it's always been. Vertical shift, still d, like it's always been. Midline is going to shift with it up and down, so it's just an equation, y equals d. What questions do you have? Okay, so this is just an introduction to the parent functions. On Monday, we're going to start to actually graph some of these. You do have an assignment that goes with this. It is in Delta Math. It's called Trigonometric Parent Functions Part 1, but it is not graphing or anything like that. I just called it the same thing, so it matched for today. It's just unit circle practice, because we still have to remember these values, or graphing is going to get real hard. Okay, does that make sense to you? Any questions at this point? All right, so hang on to this, because you're going to want to refer back to it, plus eventually we're getting to tangents.